We're going to talk about heats of formation, but before we do that, I'm going to define something we call the standard state of a substance. And the reason we do this is because defining a standard state allows us to put delta H values in tables. And we want to be able to do that. Okay, so we can do some calculations. All right, so what are standard states? We've simply defined what we want to call standard states, and everything will be listed in terms of this state. Okay, so the standard state is that all substances are listed in their most stable form. For a few examples, it's actually in the most common form, which isn't always the most stable. But those are exceptions. Okay, and at 25 degrees C and 1 atmosphere of pressure. So if something's at 25 degrees C and at 1 atmospheric pressure and it's in the most stable form, then that is its standard state. When we're talking about solutions, we're talking about 1 molar solutions is the standard state of a solution. All right, now that we've defined what is standard, we can then talk about a standard heat of formation, okay, which will be written as delta H sub F, heat of formation, and we're going to put a little symbol that looks like a degree symbol, which refers to standard states, things in their standard states. Okay, so the standard heat of formation is the enthalpy change for the reaction which forms 1 mole of a substance from elements in their standard states. Okay, so let's show an example. If we want to show the heat of formation for carbon dioxide is a gas at 25 degrees C and 1 atmosphere. And the elements making carbon dioxide are carbon, which is a solid under standard states, and oxygen, which is a gas under standard states. So the heat of reaction for this reaction is, by definition, the heat of formation of CO2, because it's forming a compound from elements in their standard states. Okay, so we can show other reactions that form carbon dioxide, like say the solid form, even from elements in their standard states, but that is not the heat of formation reaction because it's not forming a substance in standard states. Okay, so that's not the right kind of reaction. Another example that's not heat of formation reaction would be forming CO2 gas, but if it made it from something other than elements in their standard states, like from carbon monoxide. Okay, this reaction would not be the heat of formation reaction. It has to be forming the compound from elements, all of them in their standard states, and forming 1 mole of a substance. All right, for elements themselves, since the definition of heat of formation is forming them from elements, then the heat of formation for elements would be 0. Let me show you what I mean. If we want to form carbon, solid carbon, it forms from elements in its standard state, so it's forming from itself. So of course the delta H for something not changing would be 0. And same with any other substance. If you start with hydrogen gas and form hydrogen gas, of course the delta H is 0, so the heat of formation of any element is by definition 0 because it's from elements. All right, and so these results are tabulated. They're put into tables. So we have heat of formation, standard states, so it's standard enthalpies of formation, that little degree-like symbol. And so you have compounds, lots of compounds listed, and their delta H of formation at standard states listed in terms of kilojoules per mole. And these can be looked up. Okay, And we will use these tabulated values many times. All right, but for now, let's try to do some review. So I want you to try this. I want you to write the reaction. For the formation of sodium chloride from elements. In standard states. All right, and you are going to need to use that table because I want you to include the delta H. All right, so but the way you do it is you write the equation. Remember, it is forming sodium chloride, which would be a solid at room temperature and atmospheric pressure. And the elements in their standard states that makes it are sodium in the solid form and chlorine in the diatomic and gaseous form. And the delta H for that process is equal to the value in this table for formation of sodium chloride. So it's negative 411, and the units are kilojoules per mole. All right, a second thing I'd like you to answer is, what's the heat of formation? In standard states for fluorine gas. And hopefully you realize right away that it's equal to 0 because that is an element in its standard state. All right, let's look at a reaction and talk about that it's not just forming compounds from elements in their standard states, but any kind of reaction. And we can get the delta H of reaction from the heats of formation, and I'm going to show you how. All right, so remember that because enthalpy is a state function, it doesn't depend on path. So as long as we start with the reactants and we end up with the products, it doesn't matter how we got from reactants to products, the delta H associated with that will be the delta H for this reaction. So we can pick any path we want to that's convenient for us. And we're going to pick the path where all of the reactants turn into elements in standard states. And then we're going to form the products from those elements in their standard states. And we can do this because it's a useful mental exercise and will give us the right delta H. So let's start with the products. If we have elements in their standard states and we form NO from that, the delta H for that is just simply the heat of formation of NO. Because that is the definition. Elements in their standard states going to the product will be the heat of formation. Since it's the delta H, the heat of formation is for 1 mole, and we have 4, then we're actually going to need 4 times the heat of formation to do that process. Likewise, going from elements in their standard states to 6 waters will be 6 times the heat of formation of water. All right, and now you can hopefully see that when you're going from ammonia to the elements in their standard states, it will simply be the opposite in sign for the heat of formation of ammonia, because going from elements in their standard states to ammonia would be the heat of formation. So going the opposite direction is going to be negative. So we need negative 4, the coefficient, times the heat of formation of ammonia. And finally, going from oxygen to elements in the standard states would be negative 5 times the heat of formation of oxygen. And hopefully you realize that that's actually going to be 0 because heat of formation of an element is simply 0. All right, so now we have a path. We have a path going from reactants to elements into the products. So we can add up these 4 paths, these 4 parts, And that should be the delta H for the overall process of this reaction. So we can say delta H reaction is going to equal, and I'll start with the positive parts, 4 times delta H of formation of NO plus 6 times delta H of formation of water. Okay, so that's these two. Whoops. And then we have to add in the negative parts. So negative 4 times the heat of formation of NH3 minus, or plus negative, whatever you want to say it. And I can't do that now. Minus 5 times the heat of formation of oxygen. Okay, so what we've essentially done is said that the heat of reaction is equal to the sum, this symbol is a summation symbol, the sum of the product heats of formation, each multiplied by their coefficients. Okay, so that is the coefficients from the original equation, minus the sum of the reactant heats of formation times their coefficients. So this is the equation that we're going to use in general. Okay, so this part leads to this term. And remember, this is all because it doesn't matter what path we take. If you get from reactants to products any way you want to, it will give you the correct delta H. We are actually going to use another method of getting from reactants to products in another video. All right, so now we can actually solve this by looking up on a table the heats of formation for our species, NO, water, ammonia, and oxygen, although we said oxygen was 0 because it's an element. So we just have the 3, and we can add them up. So our heat of reaction for that equation above is 4 times heat of formation of NO, which is 90.3. I'm not going to write in the kilojoules because it'll make it easier to see if I don't. Plus 6 times the heat of formation of water, which is negative 285.8, minus 4 times the heat of formation of ammonia, which is negative 45.9. And then plus 5 times, that's negative 5 times 0, so that term will just go away. All right, so we get 361.2 minus 1714.8 minus a minus 183.6. So the two minuses will cancel, and our answer will be negative 1170 kilojoules. So be careful when you do problems like this to keep track of your negative signs, because it's really easy to get those screwed up, and keep track of how many times you multiply. All right, now you try one. And this is for the reaction of the combustion of ethane. Okay, ethane and oxygen makes carbon dioxide and water. We have some heats of formations given to you. I rounded them to make them a little easier to work with. And so stop the video and try to calculate a delta H, and then check your answer. All right, so the heat of reaction for this is going to be the sum of the heats of formation of the products times their coefficients minus the sum of the heats of formation of the reactants. So let's do that. You have, we'll start with the products. Start with CO2. You have 2 times the heat of formation of carbon dioxide. Try that again. I'll just leave it like that. Plus 3 times the heat of formation of water, minus, and I like to use a big bracket for all of the reactants, minus the 1 times, or just the heat of formation of ethane. I'll write it again. Delta HF of C2H6 okay, see the heat of formation of that plus 0 for the water. For the oxygen. So I'll put that all in brackets. All right, and then we can add up the numbers, or put the numbers of the values, actual values in there. Negative 400 plus 3 times negative 300 minus a negative 80 plus 0. And that gives us negative 1620 kilojoules for the heat of reaction of the combustion of ethane.